Hello everyone, and welcome to Aalto University on my behalf also. And they should be closer to my mouth. Better? So I'm Aki Vehtari and agreed to organize this StanCon. I'll talk tomorrow more about the acknowledgements for all wonderful people who's helped me. And now I focus on this model assessment and selection tutorial. This is different talk than what I gave in Asilomar. Because if it would be same, I could have asked you just to watch the video in YouTube. This is even closer, okay? Now. And so this is kind of prequel to what I talked Asilomar. So this is starting a bit slower and going in some basic things people are often asking when it's valid to use cross-validation. When I started my career and my PhD studies, the first problem I had was to predict concrete quality based on recipe, how much water, cement, what type of sand is used. So we took a photo of sand and using machine vision to analyze the properties of sand. One of the what we wanted to predict was slump, which is you get a bucket of concrete, fresh concrete, and you just pour it on the flat surface, and you can see the measure stick measuring how much it's slumped, which tells how easy it is to work with this fresh concrete. In addition, there was also like the air percentage, and this air percentage is really important for how like concrete bridges take weather, how the weather durability, and then the compression strength. And of course, I was quite worried that if my model is used to predict compression strength for concrete used to build bridges, I want them to know how accurate my model is. And I got very interested in how to estimate predictive performance. It was like last year. They noticed there were some problems with some bridges in Finland, but I was relieved to read that it wasn't my fault. It was because they had changed one of the additive ingredients and they didn't obviously update the model. So I'll come back to shifting coverage. I've also worked in predicting disease risk or cancer recurrence. And again, we have some background information on patient. We make a prediction, and it would be nice to know how good these predictions are if doctors are going to give recommendations based on these. So there's the online cancer recurrence evaluator. I think in the audience there's some people who were part of making this happen. In STAN, we recommend often to use leave and out cross-validation, and we have loop packets in R, and there are also some, at least some code for Python also. And I will explain then what are these different numbers here. And overall then the outline is what is cross-validation and especially the leave out cross-validation, uncertainty there. And very often we get these questions, can I use leave out here? Can I use cross-validation here? So I try to make this more clear. Briefly about fast cross-validation, what we use in loop packets. And related methods and model averaging, they are intentionally in a smaller font. I'm only briefly mentioning something about this. And then a bit of model comparison selection. And there was also the loop output when comparing models. I start with this very simple example of linear model. I start that we now actually know what it true mean, the true function, and also sigma, so that data generating mechanism is now that we get some x, and the line tells what would be mean of that normal distribution, and it has some scale. And here's example of data. And we can use STAN to fit linear model. And I now first show just posterior mean. And we know that this fit is fitted towards that data we saw. So if we observe another data, then we know that, okay, it can be slightly different fit just because it's fitting specifically for those observations we condition the model. And that's kind of the background why we may need cross-validation. So I'll go back to the first data and this fit. And we can use STAN to draw posterior, from the posterior distribution draws. And you see these different lines based on that. So uncertainty, and that helps also then, of course, that we have some understanding that how much this may have fitted to the data and what kind of other solutions we might get if we would have some other data. This is related to that. And we can compute posterior predictive distribution also. So for each of those lines, we have also draw of sigma, and then we average those normal distributions to get that predictive distribution. And in math, we are now integrating over the posterior distribution. With x tilde is kind of the new x, and the y tilde would be possible new observation. And this is the way we really then want to make these predictions also in this concrete, and this is risk prediction. We could then use this model to make predictions and wait for new data. We could make additional concrete experiments, wait new patients to come in, and then that way we could test that how good predictions we actually made. But then we would like to be able to test the predictive performance before we observe more data. So we can now pick one of these already seen observations and leave it out, fit a model to rest of the 19 observations. And we can see now that that leave one out fit is different because it's fitting to different data set. And now, since we are not using this left out observation, we can use it as test new data observation. We could compute just use the point estimate. So for example, for the concrete, we can make a point estimate, what's the compressive strength, and then we can compare to actual observation. And so we have here actual observations and the difference to expectation of that predictive distribution. And then we could compute root mean square error, R square, and in that concrete example, the case, I was working with the concrete expert doing her PhD thesis, and I reported then that 90% of absolute errors are smaller than certain value. And of course we can tell also that 95% of the errors will be smaller than this. And this is something that when you have that, that you are communicating to some application expert, it's very useful to use these kind of terms which are on the same scale as the measurements. And recommend to use them. And there's also, I'll make the slides available, so there's a link to specifically then also low R squared demo. But then, because we can't know beforehand what is your application and what error measure would be there good, that's why in a loop package we offer the default choice so that we look at the whole predictive distribution, leave and out predictive distribution, not just the point estimate. And it's now with the green line. And you can see that that's also, it's tilted, it's somewhere else than the full data predictive distribution. And how we then look at how good this predictive distribution is. And so this is just the equation for that predictive distribution. Here I first saw the posterior predictive density. So we are measuring, we make the predictive distribution and we evaluate it at that point where we have that test observation and compute the density there. And it's now 0.07. And then, on the other hand, now we want to actually use that leave and out predictive density, which is smaller. So here you can see the difference that how kind of using that observation to fit the model, then the full data is closer to that, and then the density is larger, and then usually we get smaller densities for left out observations. So we are a bit more surprised seeing this observation. We can then compute this density, leave and out density for all points. So we repeat the process. We leave out one of the observations, form the predictive distribution, the leave and out predictive distribution, and compute that leave and out predictive density. And now using on the predictive density scale, it is useful to go in log scale. So we just take a logarithm. You see soon nice benefit of doing in logarithms. One is of course also that sometimes these densities can be really small, so it's also then helpful numerically. Now interesting thing is that, and so we sum these log densities to get value. And this is now what we report in leave and out, ELPD_lu. So it's the log of these leave and out predictive densities. And theory says that then this is unbiased estimate of log posterior predictive density for new data. So if we would use that red predictive density, but we would use it for completely new data. We could get same, like the kind of the on expectation, the same answer. So now one nice thing about then working on also on the log scale is that if we now have both that leave and out predictive density, but we also take the log of that full data predictive density, you can see that this, so minus 26.8, it's larger than minus 29.5. And as I kind of previously said, that if you have these application-specific errors, utilities, they are more easily interpretable than these. But then the log score has the nice thing that the difference between these can be called effective number of parameters. In this case, in the model, we have 3 parameters. And in cases where we have a lot of data compared to number of parameters, it happens that this is usually quite close to total number of parameters. If we have strong priors, or we don't have so much data, then this is usually smaller than total number of parameters, but it can be used as a measure of model complexity. But you can also see that it is kind of the amount of how much the model was able to fit to the data. Some people say that they use the term overfit, but I think that's in a way not so good term, because how much fitting is overfitting? Because we want the model to fit. If we don't want the model to fit, we would not have any parameters at all. And then it would not overfit, but it would not fit. So it's fine that it fits to the data, but then again, we can also look how complex it is. Otherwise, it's not something that we need to compute that actual leave and out log score, or like the leave and out R squares, or leave and out absolute errors, or something else. It's not needed there, but it can be sometimes useful to understand something more about how complex your model is, or how some changes can affect the model complexity. So that ELPD LU, it's now the sum of these terms, but that sum of these terms were based only on 20 observations. So the question is that, what if instead of these 20 observations, we really see many, many new observations? What is our uncertainty on the actual performance on infinite new data? And it happens that we can compute it like this, so that we take the standard deviation of these log score values, and because it's for the sum, instead of dividing by square root of number of observations, we are multiplying, and then we get the measure. So we would say that if we generate more data from this same data generating mechanism, we know that there's a mean minus 29.5, and we have standard error for that how much variation we would expect seeing when we see new data. Now there's useful question now is that, what is this uncertainty related to? Data generating mechanism, we are modeling here only that conditional part, y given x. But when we think about the future, we need to think about also what are the future x's. And here links. And hi, Janne. So in this case, I had these observations equidistant and in a way fixed location. In concrete example, we also made design of experiment beforehand. So we chose what kind of recipes to use. There were different types of sand mixed together, so that there was also known that, okay, like you would like to have different grain sizes and you need to have certain amount of more rounded grains than artificially crushed grains. And so we had a mix of this, and it was design of experiment. So it was not randomly produced. And of course, when people are building bridges, they are not using those same x's, same recipes. There were intentionally some recipes which are bad, so that we can also recognize when we get bad concrete. So if we have this fixed design x, now that standard error is uncertainty only about that conditional part. Conditional part, but then averaging over all the possible locations we had. In that this is risk prediction, we can also think that there's a random process where what kind of patients we get, and we don't know beforehand what kind of patient the next patient is going to be, but there's some population distribution where the patients come, and now that standard error is also related to that uncertainty that we don't know what the next patient is. In both of these cases, whether it's fixed or random, we can also take into account that the future x's, whether they are also fixed or whether they are random, that they have different values what we had in data. As long as we are still in a working kind of close to those observations we already have. So we can handle some covariate shift, but if we think that in the future these x's will be much beyond what we've observed, then we need also more modeling. So, LU packets. I told you what is the ELPD LU and related standard error and PLU. There's also this LU information criterion. I've proposed that we would remove that. It's just -2 times ELPD LU, and there's no really need. I don't think it helps understanding. But so it's still there, but maybe it will go away. So, what if we have something like this, and then we fit data, and then we observe new data, and oops, the new data is all outside, and you can also see that it can be a bit surprised that they are not kind of following the trend. And we know extrapolation is more difficult. And the usual question is then, because of this, that can leave one out cross-validation or other cross-validation, can it be used with time series? We can use also leave one out cross-validation. So there's just now 4 different observations left out in each 4 different graphs. But since we are leaving an observation which is now somewhere there like inside, it's more easier, it's not extrapolation, it's interpolation, and it's easier to predict, but it's still something that would tell us whether that conditional distribution is sensible. So we can detect problems. Maybe instead of normal distribution, we need student t or some skewed distribution there. That can be also detected already. It's not telling us that if this is something where it's really important that we know the predictive performance for next year. So if you would be doing financial modeling and you would be making kind of betting on stock market, you would then want to extrapolate in the future. Of course, the stock market is in that way really difficult example that it's also the data generating mechanism is changing all the time. We can do a little bit better by doing one step ahead cross-validation. So now we are really predicting in the future. And we can do this then step by step, and I'll come later again these that what's the computational cost for this, but this is something we can do. And then this would be now answering the question how accurately we know the level of Lake Huron next year. And so that could affect then like whether dam is high enough or whether there's other problems. Sometimes we are interested in predicting more than just one time step. In the electric power plants, they have different scales. They want to predict next 24 hours, next day, maybe then a week, month, and so on. So there can be also different kind of that, what's the resolution, and but there can be several steps. We can do that also. So we just leave certain part of the data and then use those as a test data and only with the part data. Sometimes we can also do so that we can even use some data which is far enough in the future. It can help us learn about the data generating mechanism, but if it's far enough in the future compared to our data generating mechanism and model, it's possible that it doesn't, it's still kind of extrapolation for predicting that one step ahead. Hierarchical models. Is Lou valid then? Again, like in time series, we had different possible prediction tasks. This data is now, there are rats and the age is in weeks and there's a body weight. And you can see that clearly if the young rat was already heavier, they will stay heavier. Maybe there's even also that heavier keep growing faster. So there might be slightly the growth rate also a bit different. It is still valid again to think about leave and out if we are interested in that kind of the local conditional dependency. We might be interested in one step ahead. So this is also time series. So how about, can we predict the weight in the future? maybe we want to test overall how good our time series model is, then test at the different time locations, but leave all rats from there away. Maybe we want to leave one rat out if we want to predict how well we can predict for a new rat. This would be typical also in cases where like the 8 schools problem, where there was the coaching program for SAT tests. We would like to predict what's the coaching program efficiency for next school and not just among these. So it would be like this, leave one group out. Or we might have that actually our prediction task is that in the future we want to know how well we can predict the rest of the birth curve just knowing the initial weight. So all of these different rat examples, there might be specific prediction task you are interested in, whether it's a scientific reason or business reason. And these can be all made with cross-validation, but there's just different types of cross-validation. So you have to make some assumptions on data generating mechanism anyway when you are using cross-validation. Then it is, if you don't know so much about what would be the actual prediction task, then it's more likely that you will use simpler approaches, just leave one out or leave one group out. But then sometimes you know more about the prediction task and then can do fancier cross-validations. And like in the rats example, it's possible that we want to know different things. We want to know both how well our kind of population distribution, how good our population distribution is, how well we can generalize to new rats, but we are also want to know how good our time series model is for the growth curve. What happens if we want to extrapolate or know missing data and so on. Okay. Let's go back to still this. So, what questions do you have so far? It's a microphone.
Hello. Oh. So what if the data you have is non-representative? So the data you have may be biased towards certain populations, and you want to make a prediction against. So I'm thinking about the quite typical Mr. P situations. So you have a survey data. Maybe survey data has more data from younger people, but you want to make a prediction toward more representative data set, so that you want to make a prediction for older people as well. But if you just apply leave out cross-validations, your estimate is biased toward making an accurate prediction for younger people, just because you have more data from younger people.
Yeah, so usually in the survey you have these post-stratification approaches, and you can use those same ideas in cross-validation. When I had said that, what if you assume that it's different? Just use the same post-stratification approaches also to correct cross-validation.
Oh, I see. Great, thank you.
Yeah, that was a good question. Okay. And you can also ask later. Just wanted to give a chance to ask, because now going to next part. So we have two ways then to how to make these faster, because like in the one step ahead, we would need to do this if we have a long time series, and if we do one step ahead and then one step ahead and one step ahead. It can be quite time-consuming with Stan to fit all those models. But we have two ways then to make this faster. Again, that's simple data. And we have posterior draws with full data. And we were able to do posterior predictive distribution with the full data. And then now we can use these posterior draws from the full posterior again. The change was quite small. When we leave out one observation, the change is quite small. And that's why we can use these again. So we pick that same observation as an example. And we find out how we need to weight these to get leave one out. But these are the same lines. Only thing I changed is now alpha channel. So if the weight is 0, alpha channel is 0, which makes it completely transparent. And you can see that we are just, when I flip between these, full and weighted. And in many, many cases, these weighted draws are accurate enough for us. You can see here, so the draws, theta s, are from the full distribution. Second line, we have r, I. You have see that it's the leave and out posterior density divided by full posterior density. So we are using the same draws, but we compute these R's, importance ratios. And nice thing is that these happen to be proportional to just 1 per 1 likelihood term. So how likely it is that we observe yi given xi and the draw from the full posterior. And if we take logarithm of this term, it's something that some of you might have seen in Stan programs, that we compute this log-lick value for each observation. And this is something which is fast to compute. And then it's fast to compute these ratios. And then instead of refitting and running MCMC for all leave and out cases, we just use the full posterior draws, and for each leave and out case, compute new importance ratios. And we can then compute based on these predictive distributions. And now the predictive distribution we have there, now instead of R, I have W. And in this case, the W is Pareto-smoothed version of R. In this presentation, I'm not going in details of the Pareto smoothing, but it's something that which makes that expectation we are estimating that is more stable in cases where the leave and out distribution is quite different full distribution, so we can extend where this is work with that Pareto smoothing. But easy way now to use that full posterior draws to compute leave and out predictive distributions, and then we get leave and out predictive densities, and then we get the LPD loop. For this specific observation, when we leave it out, here's now importance weights for 400 draws. And you can see that in this case, in a way that you could assume that here, that specific observation, you can guess I chose it because it was quite far away, so this was actually one of the biggest changes happening here from the full to leave out. And it means also that there are some posterior draws from the full posterior that gets much bigger weight than the most. The red dashed line shows that what would be the size of the weight if we would have equal weight, so that would correspond then to computing with the full posterior. And so some of the weights are now larger and some of them are smaller. Usually we draw 4,000 weights in Stan by default. And the reason why I had 400 is now that it's a bit difficult to see where the largest weights are because the size of the histogram there is so small. And now you could see here, here that it seems like we have less of lines, and that's true. And we can use these information from these weights now to evaluate how much less information we have. And in this case, we get effective sample size. So we had 4,000 draws. And I should have also shown what was the effect of MC-MC autocorrelation. So it's not just drop from 4,000. There's also the MC-MC autocorrelation taken into account. But in this simple case, we were probably quite close to 4,000, and then the drop, because of using impedance sampling, gives us this. And this is still good value, so we are able to get reliable estimates. And so it is so that so we get smaller value because many of the weights are really close to 0, and some of them are much larger, and then we can compute from those weights these effective sample sizes. Another thing what we have then in blue output is this Pareto K. It's measure for how thick that tail is or how long that tail is. In this case, for this, it's 0.52, and less than 0.7 is okay, so fine. And this is something we, if you compute the Lu object and you can plot Lu object, you will get plot like this. And now I've plotted the Pareto K for all these observations, and you can see that those observations which, when left out, if the leave-out distribution was didn't change much compared to full, they have smaller K. And there were 2 observations where we are around 0.5, which is one of these kind of, so it's a kind of line that without that Pareto smoothing, we start to be in a trouble. With the Pareto smoothing, we can go up to 0.7, and then that's why there's the second line around 0.7. But this can be now used to diagnostics that, okay, that weight distribution is okay to get reliable estimates. And this is what then Lu output also is giving. That's actually not shown if all are below 0.5, but if any of them are above 0.5, then we show this summary saying good, okay, bad, very bad, and how many of those were good and how many were okay. We saw also the minimum effective sample size per category, and now there's NA because we didn't have really bad ones. But if you get these bad or very bad, then you should not trust these Syslo results, and you should use k-fold cross-validation. And here are also the effective sample sizes, and as I guessed, the best ones are close to 4,000 because the MCMC is so efficient for this simple model, and the drop is just because of importance sampling losing some information. And then the red line, you get the pluses is a bit closer. That's 10% from 4,000, and that's kind of that if we go below that, we start to also be the dangerous region, but that was also reflected already in the Pareto K. And so here's the loop package. Now they emphasize that we have the rest of the values covered. And there's also the Monte Carlo standard error of ELPD LU, and that's computed based on also these effective sample size estimates. And as you can see, that Monte Carlo standard error, it is small compared to that standard error of not knowing what's the future data and having only finite number of those observations used to compute this ELPD LU. It can be sometimes large, but it requires that you will get these bad and very bad Pareto case. Otherwise, this is usually small, but it's shown for completeness. Question about LU diagnostics.
Ready?
So just keep passing it if it's not, yep.
Where did the value of 0.7 come from for the K?
Where the values come?
No, where does the 0.7 come from? Why 0.7?
So 0.5 is that point when variance of that estimate is infinite. And then that means that central limit theorem starts to fail at 0.5, but we can manage still get useful estimates with that Pareto smoothing and based on the generalized central limit theorem. At 1 also, the mean is not finite, and at that point everything breaks down so that the convergence rate drops practically to 0. In the next version of Pareto smoothed importance sampling paper, we will have section making a connection that so Yulin Yao, also present here, realized that we can make a connection to show that what's the lower bound for the number of draws we need for importance sampling to get an error below certain desired error rate. And it's possible to show theoretically that, so that curve, how many draws we need, starts to go up, and at 0.7 it starts to go up really fast. So even if asymptotically we can manage until K1, we are in this pre-asymptotic case where things break just because we are not able to get huge sample sizes. Before that, Yuling made this connection. It was just experimentally noticed that also errors just, so with the Pareto smoothing, we get small errors until 0.7, and after that we get big errors. But there's also now really theory saying that the kind of the distributions are too different, scale divergence between them is too big, and from that it's possible to compute what's the lower bound for the number of draws we need.
Ready?
The Pareto K diagnostics tells us basically when to use or when to not use LU, right? But it also
when to not use Pareto smoothed impedance sampling.
Yeah.
So you can still do LU, but it's slow.
Yeah. Right. But it also tells us something about the model, right?
Yes.
Is the interpretation that there are large K values for observations that are outliers for the model that I have?
Yeah,
is
so
that a general?
Yeah, the observation has to be influential to get large K value. So it has to be influential in a way that the leave out and full posterior are very different. So yes, it is usually indication that you have something wrong in your model if you get large Pareto Ks, but it's also possible to make like a toy model where we know the true data generating mechanism, and it's still possible to make it so that some observations are very influential even if we have the true model. So it doesn't necessarily say that your model is wrong. It often is. It's also been, Ben Goodrich told that it's often also that there's errors in data handling often in these cases. Yeah, so necessarily it's not wrong model, but can be.
There's an example of that in the paper that Aki and I and some other people wrote that is actually, if you actually go through that paper and the code, the last section shows an example of that.
Okay,
Another question?
Yeah, but I think I should probably now go rest of my slides and then we can come back to Pareto K. It seems to be interesting, the Pareto K, but I'll... Yeah? For hierarchical models, if we are just interested in LU, we can use PsysLU, of course, for LU. Leave one group out is challenging for PsysLU. It may be that we have something for that in the future, but currently it seems to require additional quadrature integration. For time series, M-step ahead works. So here's the Lake Huron data, and here's AR2 model with prediction for there. We can start removing the last observation, use all the other observations but the last observation and predict the last one. So it's just leave one out. But then we leave two last ones, use all the others and predict just one step ahead. And you can see the Pareto case that when we leave out more and more observations and doing just the one step then ahead prediction, the problem is that if we leave more than one, the Pareto case starts to increase and sometime point it fails. But we have already in LU package also the option to, when we're running basic LU, if Pareto Ks are large, run refit only for those large K hats. And we can do the same here. So instead of doing refit 100 times, we are doing refit 7 times in a way that when the Pareto K goes too large, refit with data so far and start again doing impedance sampling, Pareto K grows too large, refit, and so on. And there's the case study for that. Other option is then k-fold cross-validation. It can approximate LU, and so it can be used where LU is used. Or it's very good for these leave one group out things, stable there. For time series, we can do leave block out things. If we approximate Lou, we should do it like this, that we assume now that kind of the left out point are not dependent with each other, and we spread evenly which we leave out, and then next iteration we leave another ones out, and then we can go through that bunch of things are left out in each iteration. If we would do this randomly, there's a danger that some of the left out are actually near each other, and then we are doing more kind of extrapolation than what we wanted in Lou. And we could do like for the groups also this random selection, or we could do these different group things, like the leave one red out, and Lou package has then these helper functions to form these data division. RStan-ARM has also a way to do k-fold more automatically, but for RStan models you need to do also a bit of coding in Stan model to handle these different training and test data sets. There are at least a couple case studies made by others showing how to do this k-fold cross-validation, and hopefully we have also someday time to make this. There's sometimes people write that, oh, I got warnings from Syslo, I used Wake and didn't get warnings, or they've heard that, oh, leave one out cross-validation can't be used because there's dependencies in data, for example, for time series, and then I use Wake. But the problem is that it has the same assumptions as law, what it predicts. So it has same exactly these kind of what is the mean for the prediction task and data generating mechanism as law, same holds for Wake. It's just that the Syslo is more accurate, it has better diagnostics, and also I think that then if you use law as a default instead of Wake, it's more obvious than the connection that what if you need to do something than law. You are thinking more about that prediction task. Hopefully you are thinking more about the prediction task. And then multiplying by 2 doesn't give any benefit, and Wake was proposed by Watanabe, and he didn't multiply by -2, but then some people still want. I'll skip this, but it's just that these are doing something then else than Wake and Lou. Marginal likelihood or Bayes factor when comparing 2 models, it's like one step ahead, but starting with 0 observations. So in these time series examples, when we did M-step and we went backwards, we stop at some point that we need to have at least some amount of data to make sensible predictions. But the marginal likelihood Bayes factor, it starts predicting the first observation just from prior. And then if you have to choose your prior also in a way that very non-informative, what would be your guess if you don't know what Lake Huron is? What would be your prior for the water level in Lake Huron? Or if I then give you some other lake, Päijänne in Finland, now go guess how deep it is. It's difficult. But then if you would have that first measurement at least, it would be much easier, and few more, much easier. So it's sensitive to prior. Okay, it seems I'm going a bit over time. So it's especially so far I've talked about model assessment, If we have application specific, we could tell that, okay, what's the absolute error for the concrete expert. It's also useful in model checking in similar way as a posterior predictive checking, I guess you heard today. Sometimes it's not needed. Posterior predictive checking can already tell here, predicting the yields of mesquite bushes. There's a left the model for weight, and we see that the posterior predictive distribution is saying that the weight can be negative. And on the right-hand side, we are predicting the log weight, and we see much better fit. There's no need now to compute log score for these models. We can reject that other model already because it doesn't make sense to predict these negative values, especially when there's so much master. Model comparison. Before you use cross-validation, think whether you could just analyze posterior distribution of more complex model directly. The beta blocker example has treatment control group comparing them instead of making simpler model that the treatment and control have the same parameter, the common parameter. Just look at the model where they have different parameters, compute odds ratio, look whether that's far away from one. So there's the case study. This one, then I needed quickly some small data, and this is also in a Loo package vignette, but originally the example is from a statistical rethinking. And so primates with larger brains produce more energetic milk. And then there's the percentage of neocortex mass, an alternative model, also the log mass. We have ELPD Loo, and now instead of just comparing these sums, 3.7 and 8.4, because with this we have a kind of problem how we didn't compute the standard error. We need to compare these point-wise. It's often common that same observations are difficult to predict for both models. But if we compare the standard error for the difference, it's better, and that's what we get reported if you use compare or compare model function in Loo or RStanArm. When we get the difference and some standard error, here also, then people want to know often that is this difference significant? We intentionally don't report any probability for that. One problem is that this standard error is difficult to estimate accurately, so it's a bit optimistic even. Again, if one is not clearly better than others, again, maybe you should have a continuous expansion including all models, or Bayesian model average inversion, and then look at again the posterior. So you should include in a way then both if you can't make a decision which one to use. In a nested case, the simpler model is included in the more complex model. And you could choose simpler model if you have some cost for making measurements in the future or explaining it to doctors. But unless you know these, that you have some cost, it would be better than to choose the more complex model, because then it's a better presentation of your uncertainty. If you are uncertain whether you should include something, Bayes' theory says that include it and compute uncertainty for that and integrate over that uncertainty when making predictions. especially do not use cross-validation to choose from a large set of models. It's fine if you have small set and if it's saying that they are clearly different, yes. Look at the projection predictive approach. There's a link to the extra material, and there's the Asilomar video talking about projection predictive approach. You can watch that. So in a way, I made beforehand the videos you want to watch after this. Just one slide about Bayesian stacking Lu weights. So they are useful for doing the model averaging in case of Stan when it's difficult to do compute marginal likelihoods and doing the usual BMA, or if we assume model misspecification, as you can read in that paper. Don't use these Lu weights or Bayesian stacking weights for model selection. You can drop models which get 0 weight, but if you have uncertainty, I would prefer that you don't choose someone which has the weight 0.9. You should integrate, you should combine model with 0.9 weight and 0.1 weight. So last slide. So it's good to think predictions of observables, because observables are the only ones we can observe. So in a way that we can't usually observe the true parameter values later. And then that's why it's good, but we often can observe more data. Of course, like Richard works in the anthropology. It's unlikely that he could observe more data from these studies he's working on, like the ancient civilizations and how many tools they have developed. Difficult to replicate. But still, it can be useful to just think that what if I could get these new observations? Yeah, so we can use cross-validation to simulate that prediction and observing new data. It's especially good if you don't trust your model, because it's kind of making very weak assumptions on the future data. Just these weak assumptions on data generating mechanism. Different variance, useful in different scenarios, and it has high variance. So there are cases where you can do better if you can trust your model. Okay. We are over time, but we have time for questions. Yeah. And so let's have 2 questions, and then you can ask more later today.
What is the status of generating ARMA?
Sorry, say again.
What is the status? You showed the case study with the time series predictions with the R model. What is the status when you coded the more advanced models, like different versions of that?
So in a way, it shows how to do it also for more complex models. It's not the kind of the code we have. It's not AR2 dependent. It's just that we don't have yet kind of ready-made package functions, so you will still see kind of explicitly what we are doing, but you can easily use it for other models.
Yeah, last question.
So there were a couple guys with hand up earlier. Did your answer get answered already? Or you are hungry? So the get together tonight, there's these tapas, so Finnish tapas, and you might want to then eat after or before, so you will get some food there, yes, but if you know that you usually need big person. You may need to.
Tomorrow there's a
somewhere else.
full dinner, right?
And tomorrow, don't come here tomorrow. So tomorrow, it's Töölö campus in Helsinki. And I hope I'll see you all in Get Together.